Welcome back, students. In this video segment, we will take a look at section 12.3, the dot product. So actually, in this video segment and the one coming up, we're going to continue our look into the algebra of vectors with two additional kinds of multiplication. In the last section, we looked at scalar multiplication. Remember, a scalar is just a fancy name for a real number. So if for example, A is the vector whose components are A1, A2, and A3, and if K is an element of, fancy looking little e that didn't turn out real well. It's actually, I believe this is just a small epsilon that's morphed into the symbol for an element of. So if K is an element of real numbers, or if K is a real number, then from the last section, we define Ka to be the vector whose components are K times A1, K times A2, and K times A3. And before we did that, we looked at the geometry of what multiplying a vector by a scalar is or does. If we multiply a vector A by K, it either stretches the vector, shrinks the vector, or does one or both of those things in addition to flipping the vector or reversing the direction of the vector. Okay, so multiplying a vector by a constant K scales the vector to a different size while retaining the direction of the vector in terms of the direction of the vector not changing. Okay, so in this video segment, we're going to take a look at the dot product. The dot product is also called the scalar product, not scalar multiplication, but it's called the scalar product. And the reason why it's called a scalar product is that this dot product, the end result, is a scalar. The end result of the dot product is a scalar. Okay, so let's take a look at what the dot product looks like. So let's let B be the vector whose components are B1, B2, and B3. We define the dot product as A dot B, and it simply equals A1 B1 plus A2 times B2 plus A3 times B3. Okay, and you notice the result of the dot product is a scalar. This quantity, A1 B1 plus A2 B2 plus A3 B3, that is a scalar quantity. It's not a vector quantity. Whereas the kind of multiplication we talked about in the last section, scalar multiplication, produced another vector. Okay, so note, before we look at an example, note there is no such thing as a vector B with no dot between or no symbol between for multiplication. There's no such thing. This is meaningless. One of the biggest problems on the first exam in a third semester calculus course is that students get lazy with notation. You can't do that. If you want to multiply two vectors together, you have to put a symbol between them. And in this section, the symbol is the dot. Okay, so just while we're at it, there's no such thing as a vector and then parentheses B vector, or A vector parentheses and then times B without parentheses, or A vector, there's no such thing. These things just have no meaning whatsoever. So the upshot of this is that we have to be extremely obsessive over notation. We have to be very, very careful with notation. So here's an example. Once we're set on the notation, finding the dot product is extremely, extremely simple. So find A dot B, for example, if, let's say part A is the vector whose components are -1, 0, and 2, and B is the vector whose components are 3, -4, and 5. I just made those up just now. So A dot B is very simple. You take the first component of A, multiply it by the first component of B, plus the second component of A, times the second component of B, plus the third component of A, times the third component of B, and then compute the arithmetic. This is -3 plus 0 plus 10 or 7. 7 is a scalar, so that's why we call this a scalar product. Let's take a look at one more before we move on. Part B, A is the vector -3i plus 4k minus 2k. So I'm getting the vectors in terms of the standard basis vectors that we talked about in the last section, rather than component-wise with the bracket notation. So B is the vector -i plus 3j. Okay, well, where's the third component of B? It's there. It's 0k. So this vector, the vectors A and B are both in 3 space. By the way, in order to find the dot product of two vectors, the vectors have to come from the same space. So you can't dot a vector from R3 with a vector from R2. Makes no sense. Makes no sense. Okay. So A dot B, but you can certainly take the dot product of two vectors from R2, okay, or R3. Okay, so A dot B is the first component of A times the first component of B, plus the first component, a second component of A times the second component of B, plus the third component of A times the third component, 0, of B, and we get 3 plus 12 is 15. Okay, I think we should look at one more. A is the vector -3, whose components are 4, -3, 4, and -2. The same A is above. And B is the vector whose components are -1 and 3. So I want you to tell me what, if you can tell me right away, if you can say right away, what is A dot B? It looks like we're dealing with the same vectors as in part B. We're not. The answer is not 15. The answer is not 15. The vector B is a vector in R2. In order to have B with those first two components in R3, we would need to write B as a vector whose components are -1, 3, and 0. So the vector A is in R3. A is an element of R3. But B is an element, a vector in R2. So A dot B is undefined. Undefined. Okay, so there's a little danger with the different notations. Before, I had in part B, I had the vector B as -i plus 3j. What space is that vector in? The answer is it's in whatever space you want it to be in, either R2 or R3. If you interpret it as R3, then the vector can be interpreted as negative I plus 3j plus 0k in R3. If it's interpreted as a vector in R2, it's negative I plus 3j. So it can be in either R2 or R3. However, the vector B, let's say B1, this would be a different vector, negative 1, 3, that's the same thing as the vector above. This is in R2, the vector B in above. B and B1 are the same vectors, okay? And you can't interpret the vector that only has two components in bracket form as a vector in R3. I think you should hear that again. You can't interpret the vector in component form with only two components as a vector in R3. It's in R2. If you want it to be in R3, you would have to write it as negative 1, 3, 0, R3. Okay. So since we're labeling vectors here, the original B sub 3 is in R2. B sub 3 and B sub 1 are the same vectors that I have here. The vector B, sorry about this backwards numbering, but it'll get the job done. V4 is interpreted to be in R3 because I've added the 0k onto that, indicating that it's in R3. But I don't have to. I can interpret B3 as being in R3 if I just assume that the third component is 0, or the coefficient of k is 0. So let me summarize this, because I think it got really much more complicated sounding than it is. If you use the standard basis vectors and your vector has only two of the standard basis vectors I and j, you can interpret that as being in R2 or R3. However you want. You put your own context to it. But in bracket form, only vectors with three components are in R3. Physically writing three components in R3, and negative 1, 3 is in R2 because it only has two components. Okay, I hope that doesn't confuse things too much. If not, send me an email and I'll try to clear it up for you. Don't hesitate, please. Don't be shy with emails. Okay. So on page 847 in your textbook, your author lists some properties of the scalar product. On page 847, you need to familiarize yourself with those properties. They're going to follow you through your STEM math, which basically means they're going to follow you through physics and calculus. And if you're an engineering major, through engineering. Vectors are central in engineering. Okay, so the first product, or the first property, says that A dot A. There's no such thing as a vector A squared. There's simply no such thing. But we get something close. A dot A is the magnitude of A squared, not A squared. There's no such thing as a vector A squared. There is simply no such thing. Don't write it. If you write it on a test or whatever, it's just wrong. It's a really huge source of point loss on the first exam is the misuse of notation. So be very careful with notation. Be obsessive about it. So A dot B is equal to B dot A. That's true. That's true. Well, just look at the definition of the dot product. Look at the definition of the dot product. Way above here. It's not too far above. Let's see if my surface is going to allow me to get up there. Look at the definition there. Look at the definition of the dot product. If you want to compute A dot B, you have, let's change it to, let's say, red. You have, that's the product, that's the definition. So if you had B dot A, the only thing that would do is it would rearrange the order in which we multiply the components. It would be B1 A1 plus B2 A2 plus B3 A3. There, you would get exactly the same thing. Okay, so back to our properties. It's also easy to see number one. Very easy to see. If you have A dotted with itself, that's A1 times A1 plus, let me rewrite that. That's just a little too sloppy on this side for my liking. That is A1 times A1 plus A2 times A2 plus A3 times A3. That's A1 squared plus A2 squared plus A3 squared. That's exactly the length of A squared. If I put the square root on it, that's the length of A. And if I square that, the square root disappears. That's the length of A squared. That should be familiar to you now. If it's not, then you probably haven't finished homework from the last section. Okay. As I say, sort of semi-sarcastically. Okay. The third property, we have a distributed property. We have a distributed property, A dot B plus C. This is A dot B plus A dot C. Okay, that's pretty cool. 4. If you take A and scale it either longer or shorter, that means multiply by a scalar. Now that result is a vector. CA is a vector, so we can dot it with B. This part of the property says that C can be done last. You can find A dot B first and then multiply by C. Be careful here. The products that are occurring on the left-hand side and on the right-hand side are not the same. The multiplication that's occurring, the multiplication right here, this is different from the multiplication that's occurring right here. Okay, these are different multiplications. Different. I'm dotting my E's. Different multiplications. Different products. Look on the left. CA is scalar multiplications of a vector. Okay. Now on the right, A dot B, that's a scalar. It's just a number. And C is also a scalar. So this is the kind of multiplication that separates C and A dot B. That's the kind of multiplication we grew up with in algebra. That's scalar multiplication. Not scalar multiple of a vector. It's regular scalar multiplication of numbers. Okay. So really these formulas, while they look simple, they've got some stuff going on. There's that we need to be careful of. There's a third part of this. This property also says that I can also move the constant to B and then take the dot product. I can multiply B times C, the scalar C, and then dot the product, dot with that with the vector A. Okay. 5. Here's a really good one. This is really, really, really good. Okay. So, what is 0, vector 0, dotted with the vector A? Okay. Now, before you jump to an answer, is the result a scalar or a vector? No. Look at the dot. Dot says that the result is going to be a scalar. So the answer is it's 0. Okay. Now I have a little exercise for you that's going to help you on your first exam. Very likely help you on your first exam. Fill in the blanks. Example. I'm putting this in green because it's kind of important here. Fill in the blanks. Fill in the blanks. So, 0A equals what? 0 vector A equals what? 0 dot A equals what? How about 0 dot A equals what? Okay. So the first one, that's a scalar multiple of a vector. Scalar multiplication, scalar multiple of a vector. Remember, the scalar multiple of a vector scales the vector, but retains its direction. So 0A, is it a vector or is it a scalar? So to write 0 would be absolutely incorrect. 4 points lost on a test if you fill in the blanks with the 0. If you multiply a scalar times a vector, you get a vector. How about the vector 0 times the vector A? This is undefined. There's no such thing. There's no way to separate two vectors. There's no way to multiply two vectors without an operation between. Undefined. There's no such thing. How about 0 dot A? Also undefined. No such thing. 0 on the left is a scalar. 0 on the left is a scalar. A on the right is a vector. The dot product takes two vectors, is a product between two vectors. So undefined. About 0 dot vector 0 dot vector A. Well, that's 0. We just looked at it. This is a very, very, very good exercise for you. Okay. Next. We're going to look at an alternate formula for A dot B. Okay. In order to do that, we have to define what we mean by the angle between two vectors. The angle between two vectors. Right now, it should seem the concept of an angle between two vectors, unless you've seen it before, should seem really obscure or strange, because what are vectors? They're arrows. There's the vector A, here's the vector B. They're arrows in space. Remember, that's the geometric, that's a good, powerful geometric definition of vectors. Yeah, they're just arrows in space. So what do you mean by an angle between these two vectors? Well, this is how we define the angle between two vectors. To find the angle between two vectors, we take the vectors and move them. We move them so that they're positioned tail to tail. Okay. So now we got two pretty obvious possibilities. Is this the angle between the vectors? Or is this the angle between the two vectors? The bigger one. Which is the angle between the two vectors? Which is the angle between the two vectors? Theta 1 is the angle between A and B. Vectors A and B. Theta 2 is not. So we define the angle between the two vectors to be the smaller one. Okay, so the angle between two vectors is always between 0 and what? Pi. Between 0 and 180 degrees. It's always. So if you find an angle between two vectors that's 181 degrees, that's wrong. What would be the angle between the two vectors if you find 181? It would be 179. It would be 179. It would be 360 minus 181. Okay. So why do we need an alternate formula? I haven't given you the alternate formula. Why do we need an alternate formula for the dot product? Now here's one good reason. Example. Find A dot B. And here's A. Here's B. Here's B. And let's say it has length. What do I want it to have length? 4. And here's A. And I want A to have length 3. and the angle between the two vectors is 45 degrees. How in the world am I going to use the formula for the dot product that we have above? How in the world am I going to use the formula A dot B equals A1 B1 plus A2 B2 plus A3 B3? I can do it. It's not going to be fun, but I could do it. I could probably put a set of axes in here, impose a set of axes, and put the vertex of the angle formed at the origin. I could find components, etc., etc., etc. I could do this, but it would take quite a bit of time. Okay, a lot of algebra. There's a way around that. So here's the alternate formula for A dot B. Right now, that A dot B is equal to the length of A times the length of B times the cosine of the angle between the two vectors. Okay, this in a lot of physics classes, this is the first definition. This is how they actually define the dot product. This is very often. I would imagine, because in physics, the first application of the dot product is going to be to study this thing called work, and we're going to see that the whole reason for the discovery of this dot product is to make the discussion of the physical quantity work manageable. So we'll see that in a bit. But this is the alternate definition. So now let's go back to the previous problem. Let's find A dot B. So A dot B, by this alternate formula, is the length of A times the length of B times the cosine of the angle between them. Well, the length of A is 3. The length of B is 4. That times the cosine of 45 degrees. Or 3 times 4 times radical 2 over 2, or 6 radical 2. Just checking to make sure I believe what I wrote. Yeah, 6 radical 2. We don't have to bother with finding components of A. Very, very important. Okay. So there's another important use for, there are a whole bunch of important uses for the dot product or the scalar product, but here's another really, really powerful one. Let's take a look at a true or false question. Example: true or false? True or false? A. If X and Y are scalars, real numbers, and if X times Y equals 0, then either X is going to have to equal 0 or Y is going to have to equal 0. This is not a true or false question that might arise in this course necessarily. It would probably arise in elementary algebra or pre-algebra. If you multiply two numbers to get 0, then this is saying that then one or both of those two numbers has to be 0. Of course, this is absolutely true. Absolutely true. So if A and B are vectors, and if A dot B equals 0, then A must equal the 0 vector, or B must equal the 0 vector. Well, it looks like it should be true, because if A is 0, definitely we get A dot B equals 0. If B is 0, then we get A dot B is 0. That's not what the question is saying. It's saying that if we have A dot B is 0, the result is 0, the product, then the two vectors, one or both of the two vectors must be the 0 vector. This is absolutely a false statement. Absolutely false. Okay, I want you to consider A as the vector whose components are 1 and 1. So we're looking at two vectors in R2, and B is a vector whose components are -1 and 1. So what is A? What is A dot B? A dot B is 1 times -1 plus 1 times 1, which is -1 plus 1, which is 0. But neither A nor B is, and I'm having a grammar crisis, is the 0 vector. Let me just write the 0 vector. Let me erase that. Neither A nor B, I know how to get around the grammar, equals 0. Nah, I don't like that. It looks like I'm saying B equals 0. Neither A nor B is 0. Okay, so we don't require that A or B is 0 if we have that A dot B is 0. Now there is something geometrical that's happening here that we want to look at. I want us to look at the vectors A and B that I have considered here. Here's the vector 1 whose components are 1 and 1. Here's A, drawn as a position vector. Now here's the vector B, drawn as a position vector. The angle between those vectors is 90 degrees. Okay? So, if A dot B is equal to 0, then it could be that A is 0 or B is 0, or it could be that those vectors are perpendicular, okay, or orthogonal. They're called orthogonal. So here's the bottom line, very important bottom line. If A dot B equals 0, then A could equal 0, the 0 vector, or B could equal the 0 vector. Or A and B are perpendicular. With the new word orthogonal as a possible word for another word for perpendicular, orthogonal / perpendicular. So it's a way to determine if you have perpendicular vectors. If you find that if you find the dot product of two non-zero vectors is 0, then they've got to be perpendicular vectors. Okay, this is true. This is a hugely important conclusion for us. That the dot product measures the dot product can measure whether the vectors are perpendicular. Now, let's take that one step further. Let me get back into a black pen here. What can you tell me about A dot B? A dot B. And I'm not even giving you the length of the two vectors, either of the vectors. A dot B is length of A, length of B, times the cosine of the angle between the vectors. Now, the cosine of, theta is between 90 and 180. Theta is between pi over 2 and pi, and if theta is in the second quadrant, between pi over 2 and pi, then the cosine is less than 0. If theta is in quadrant 2, then the cosine of theta is negative. So A dot B is less than 0. So what can you tell me about A dot B now? I think you get this one right away. I'm assuming that the angle is 90 degrees, so A dot B is 0. Okay, it doesn't look like 90 the way I've drawn it, but it's supposed to be a 90 degree angle. Here's A, here's B. What can you tell me about A dot B? Well, it's length of A, length of B, times the cosine of theta. But theta is an acute angle, so this is positive. Cosine of theta is positive. So A dot B is greater than 0. So the dot product can be used to measure the extent to which A and B are orthogonal or perpendicular. So if the angle is between the two vectors is more than 90, the dot product is negative, is equal to 90, then dot product is 0, and less than 90, then the dot product is positive. Okay. So here's a quick little summary. We've looked at two kinds of vector product or products involving vectors. The first is called scalar multiplication of a vector. Scalar multiplication of a vector. It means scalar C times a vector A. And the result is that we get a vector, and the resulting vector is going to depend on whether the constant is positive or negative. If the constant is greater than 0, then the resulting vector CA is either going to be longer than A, have greater magnitude, or less, or shorter than A, have less magnitude, depending on whether C is greater than or less than 1. If C is negative, then we get the same situation, but the direction of A is reversed. So multiplying by a positive scalar stretches or shrinks the vector but keeps the same direction. If the scalar is negative, then the vector is either stretched or shrunken, but pointing in the opposite direction. On the other hand, the dot product of two vectors, the scalar product of two vectors, doesn't produce a vector, it produces a scalar. And I've rewritten the two formulas we have for the two very popular formulas we have for the dot product, and a kind of nice geometrical result we get from the dot product. If the dot product is positive, then the angle between, rather, let me say it this way, if the angle between the two vectors is acute, then the dot product will be positive. If the vectors are orthogonal, then the dot product will be 0. If the angle between the two vectors is more than 90 but less than 180, then the dot product is negative. Okay, so let's move on. We're not talking about anything outside of the scalar product. We're still talking about the dot product, but we want to talk about two aspects of the dot product. One of them is the most important reason why we have the dot product. Okay, so let's do that. And to do that, I'd like to talk about these two things called projections and components. First of all, projections are vectors, and components are scalars. Okay, so here's what I mean. I think the best way to do this is by drawing an example. So here's a vector. Here's a vector. Let's say a vector A. And let's say I have another vector B, and I draw that vector B so that A and B are tail to tail. And suppose I drop a perpendicular from the tip of B to A. So this is supposed to be 90 degrees. And I draw in green this vector in green. And suppose that vector turns out to be 3i plus 4j. Really doesn't look like the vector 3i plus 4j, but let's just assume it is, okay? Okay. Here's a non-technical way of looking at the projections of components. The component of B in the direction of A, so component with subscript vector A, the component of B in the direction of A is 5. Okay. The projection of B in the direction of A is 3i plus 4j. Okay. And notice that the length of that projection, the length of 3i plus 4j is 5. Okay, so right now it looks like the projection is a particular vector and the component looks like the length of that vector, but it's not quite. It's not quite there. Not quite. Okay, so here, let's take a look at another example. Here's the same vector A. Move this up a little bit. Here's the same vector A as before. But we have a new vector B. The vector B is this vector. And if I come backwards along in the direction of A, see, A starts at the vertex. So if I come backwards, and let's say I get a vector B is this vector. This is a vector. Oh, that's not a vector B. That's just our the green vector. We'll just call it is negative 3i minus 4j. Okay. So here are the quantities. We have two quantities associated here. We have the component of B in the direction of A, and we also have the projection of B in the direction of A. The projection of B in the direction of A is the negative 3i minus 4j. So the projection doesn't actually have to project onto the vector. It could project in the opposite direction of the vector, but it still projects along the vector A, the line that we could place right on top of the vector A. Now here's the big difference though. The component is negative 5. The component is negative 5, even though the length of negative 3i minus 4j is positive 5. The component is negative. The component is negative. Okay? So the component being positive or negative is going to depend on whether the two angles A and B or the angle between the vectors A and B is less than 90 or greater than 90. So if the angle between the vectors A and B is more than 90, but of course less than 180, then the component's going to be negative. The component is positive if the vector B projects directly onto the vector A, if the angle between the two vectors is less than 90. Okay. So I want a formula. I want a nice formula for both these things. I would like a formula for both the projection and the component. So that's what I'm going to develop for you right now. So here's a vector. Oops, I'd rather have it in black here. Where's my computer will let me do that. I'll probably have to erase it first. Okay, so here is A. Here is B. I would like a formula for the component of B in the direction of A. So I want to project B in a perpendicular fashion onto A, and I want to find the length of that projection. Okay, and it will be length. It'll be a positive quantity since in the way I've drawn this, B is projected directly onto A. The angle is less than 90. Okay, so I'm going to put the angle theta in. I'm going to use some trig here, some easy trig. The component of B in the direction of A, if the magnitude of B is the magnitude of this sort of little right triangle, then the component of B is nothing more than the length of B cosine theta. Well, we can see that we can possibly get a negative number out of that. If theta is more than 90, cosine is negative, so that's cool. But this isn't really an effective formula. I would like a formula that doesn't require that I find the angle theta between the two vectors. So I'm going to use a trick. What I'm going to do is I'm going to take this quantity, and it's a perfectly good formula for the component, that length of B cosine theta, but it's just not real efficient for us. What I'm going to do is I'm going to multiply it by the length of A, and I'm going to divide it by the length of A. Okay, it's a neat little trick I'm doing here, by the way. Do you recognize the numerator now? The length of A times the length of B times the cosine of the angle between the vectors. That is nothing more than A dot B. And the denominator is length of A. It's a very nice short formula for the component. That is a nice formula for the component of B in the direction of A. Okay. So now what I'd like to do is I'd like to find a formula, a correspondingly simple formula if possible, for the projection. What's the projection? It's this little green vector here. That green vector, that's the projection of B in the direction of A. Okay, and I'm going to use another little trick. These neat little tricks. First, I'm going to find a unit vector. Remember we talked about unit vectors. I'm going to find a unit vector in the direction of A. Okay. How can I construct a unit vector? That unit vector is going to be red. Oh, let's say blue. How can I construct a unit vector in the direction of A? Well, not tough. If I take the vector A and multiply by its reciprocal, you can kind of write it as A divided by the length of A. Okay. That's really kind of bad notation because we don't have vector dividing a vector by anything. It's really 1 over length of A times A. But this notation is allowed. This is allowed. It's very, very common. Okay, so there's a vector, the little blue vector I have pictured there. That points in the direction of the projection, but it's not long enough. So stretch it out. Stretch it out by how much? Stretch it out by the component that we just found. And I want to say that again. I took A, and I computed a unit vector in its same direction as A by dividing by its own length. Now I want to take that length 1 vector, that unit vector, and stretch it out to the length B. The projection, rather, of B in the direction of A. So I'm going to do that right now. So the projection of B in the direction of A should be, well, I'm going to take that unit vector and stretch it out by the value of the component. It should just be the component of B in the direction of A. That's a scalar. times the unit vector times A over the length of A. So it's a little more complicated of a formula than the component, for the projection of the component. But we can simplify this a little bit. This is A dot B over the length of A squared times A. Okay, and this is our working formula for the projection. These two formulas are extremely important. They're in a long list of formulas coming up for our course. I think I'll highlight them in green. I don't know why. Just want them to show up separately. Okay. So let's take a look at a specific example using these two formulas. So here's our next example. Find the component of B in the direction of A and the projection of B in the direction of A if the vector A is the vector whose components are 4 and -2, and B, and also a vector in R2, is a vector whose components are -1 and 3. Oops. Sorry about that. Okay. I drew the two vectors as position vectors because I'd like to actually see geometrically what these quantities are giving. Okay, so let's do this. Let's take a look at the algebra of this, okay, using the formulas. Well, both the formulas are going to require A dot B. So A dot B is 4 times -1. Multiply the first components of each vector together, and then add to that the product of the second components. And we get -4, take away 6 more, we get -10. Okay. Now, moving forward, we're going to need the length of A. The length of A is the square root of 4 squared plus -2 squared. Okay, or the square root of 20, or 2 radical 5. So the first quantity, the component of B in the direction of A, the formula we developed was A dot B over the length of A above. Mind you, A dot B in green on the right, upper right, over the length of A. Okay, well, A dot B we've just figured out is -10. The length of A is 2 radical 5. This is the same thing as negative, let's see, make sure this is, I believe this. This is approximately equal to -2.24. Now, does it make sense that it's negative? Yes. Now, the reason why it makes sense that it's negative is if you extend a line along A and project the vector B along that extended line, the angle between A and B is more than 90, so the projection is actually behind A. Remember, that gives us that the component should be negative. Okay, so that -10 over 2 radical 5, or -5 over radical 5, actually that's equal to negative radical 5. That's about -2.24. So this makes sense. And even my drawing, I'm not very good at drawing. You're going to discover that more and more as we go along. It looks like it's about 2 in length, 2 and some. It looks about right. That little length behind looks about 2 point something. Okay, and it's definitely negative. So the projection of B in the direction of A. So that's going to be a vector quantity. What can you tell me about, what do you expect for the components of that vector? Should they be first negative, second component negative, first one negative, second component positive, both negative, what? No, the projection, I'm going to draw it here. The projection should be this green vector. So I would expect the first component to be negative and the second component to be positive. Negative and positive put me into quadrant 2, remember? Okay, so the formula that we just developed for the projection is A dot B over the length of A squared A. Okay, referring to above, A dot B over length of A squared A. A dot B is negative 10. The length of A is the square root of 20, so the square root of 20 squared. And A is the vector whose components are 4 and negative 2. Okay, so this is negative 10 over 20, that's negative 1/2 for vector whose components are 4 and negative 2, or a vector whose components are negative 2 and 1. It looks like I got sort of close. Negative 2, really stretch here. If you look at a vector whose components are negative 2 and 1, it looks like the green vector is it's in the ballpark. This is a good example for you to get used to the product, the projections and components before you dig into homework and stuff. Okay. Now what we're going to end with is the first reason that I know of, the first reason for the existence of a dot product, and it comes from physics. And if you've had physics, this is going to be old news for you, but you might learn something new from it. If you haven't had physics, there's a quantity in physics, and it's a scalar quantity called work. Okay, so let's develop a formula for work. The quantity in physics called work is central in that part of physics that deals with mechanics. And that's a big chunk of physics, a big chunk of early physics. Early physics for students. Now, I'm going to develop the concept of work without vectors, then we're going to get vectors involved. So here's our physical situation. We have a very tall refrigerator that somebody's going to push. I'm going to put a real small guy right here. The guy's going to push the refrigerator. Push the refrigerator. Okay. The refrigerator starts at this position, and when the guy is done pushing the refrigerator is now in this position, and the refrigerator has moved 3 feet. Okay, so the refrigerator is moved 3 feet. We're also going to assume that the person pushes in the right-hand direction with 5 pounds of force, 5 pounds of force in the horizontal direction. So I'm not bringing vectors in here. It looks like I'm sort of close to bringing vectors with that little arrow, but so that's all right. Work is going to be 5 pounds times 3 feet, or 15 foot-pounds. So the units of one set of units for work are foot-pounds. Foot-pounds. If you're in the metric system, then it's Newton meters. Newton meters. Okay. Foot-pounds, Newton meters. Okay. So let's get some vectors involved here. Same situation. Same refrigerator, Same initial and final positions for the refrigerator. The person is still applying 5 pounds of force, but I'm going to get a vector in here. I'm going to represent the vector by this little red arrow. That is the force vector. And we know that the length of the force vector, the magnitude of the force vector, is 5 pounds. And I'm going to introduce another vector. I'm going to introduce, let's say, a vector in green from the center of the refrigerator in its initial position to the center of the refrigerator in its final position. I'm going to call that green vector D for displacement. Okay. Displacement. Okay. And since it's moving to the right, displacement vector will be to the right or whatever. All right. So we're going to redefine work here. Work is now the length of the force, magnitude of the force vector times the magnitude of your displacement vector. Nothing changes in terms of the result. The magnitude of the force is 5, the length of the displacement vector is 3, we get 15 foot-pounds. Foot-pounds. Okay. Now we're going to change things up a little more. We're going to keep the same situation in terms of moving the refrigerator from the initial position to the final position. Looks like the refrigerator got bigger, but that's all right. So same, now it got smaller again. So we still have the same initial and same final positions. We're still looking at a displacement vector D. However, this little guy is no longer going to push with the vector, push the refrigerator horizontally. This little guy is now going to push the refrigerator in this direction. Why would he do that? That's not really a wise decision. It's going to take more effort on his part. More what? More work on his part. But you could push the refrigerator at that angle, and it would move to the right. It would move to the right. But the work involved in doing that is only the only contribution of his force to the work amount, the amount of work required to move the refrigerator from the left position to the right position, is the component of force in the direction of motion. I need to say that again. Only the part of the force vector that contributes to work is that part of the force vector experienced by the refrigerator. The refrigerator, if it can feel, is going to feel some push. But the only thing that contributes to the amount of work required to move the refrigerator from the left to the right position is that component of that force in the direction of motion. I'm going to say that again. Suppose the angle now is 45 degrees. The angle between the displacement vector and the force is 45 degrees. That we're still applying 5 pounds of force, so the magnitude of the force is still 5. But work is only the only part of force that contributes to work is that component of force that is in the direction of motion. So work is equal to only the part of the force that contributes to that in the direction of motion is the component of force in the direction of motion times the displacement, the magnitude of the displacement vector. Only that part of the force experienced by the refrigerator in the direction that the refrigerator is going to move is going to contribute to work. Okay. Now we have a formula for the component of force in direction of of displacement. It's F dot D over the length of D. That's replacing A and B with D and F, respectively, times the displacement vector. Length of the displacement vector. Look what happens with the magnitude of the displacement vector. This is probably the most important result of the whole section. It's a purely physics result. The work required to move the object from through a displacement vector D is equal to the dot product of the force with a displacement vector. This is the reason for the dot product, the first reason for the dot product. Let's get an answer out of this. So the F dot D is the length of F times the length of D times the cosine of the angle between the two vectors. The length of the force, the magnitude of the force is 5 pounds. The length of the displacement vector is, I think it was 3 feet, times the cosine of the angle between the two vectors times the cosine of 45 degrees. So this gives us 5 times 3 times radical 2 over 2, which is 15 radical 2 over 2, and that's about 10.6. 10.6 foot-pounds of work. Okay. So this was a long section. The entire section involves only one product, and it's the dot product of two vectors, A dot B. And along the way we discussed components and projections, and ultimately the reason for the dot product, the first reason for the dot product is the quantity work. And it brings us to the end of our segment. So I'm looking forward to talking with you all again soon.